Hello, I'm Weiwei. I work at Mojo language team at Modular. Today I'm going to have a quick talk, lightning talk about Mojo GPU compilation. So Mojo is the Pythonic system programming language that we're building at Modular. It looks somewhat like Python, but it also has a lot of superpower kind of features for support for generic programming, a strong type system, and memory safety. It is, we believe, a best way to extend Python to both CPUs and GPUs. It is very fast. It's Python, but it's like C or C++ kind of performance. It is also one of the bedrock for Modular's MAX inference engine. One of the features that we are really help us building stuff internally and also get more and more interest from the community is that Mojo provides a unified programming model for both CPU and GPU. So you can unlock the full power of a standard CUDA and ROCm, but you do not necessarily have to use we do not actually use the vendor toolkit to get those performance features. So you can still have threads and walks and the WMMA instructions written in the Mojo library without having to use CUDA. And all of the GPU kernels that we have are written in Mojo, and they are scalable for different GPU vendors, including NVIDIA, AMD, and Apple. Most of the GPU features are actually part of the Mojo standard library, so they are Mojo code instead of compiler magic, so which also makes the compilation much, much faster. So this is how kind of a unified Mojo program look like with a GPU kernel defined at the beginning of the program and the CPU driver code that we get the device context, we create the buffers on the device, and then we do this enqueue function call. We provide the kernel function as a parameter to that function, and then underneath the compilation, you will compile the kernel and launch the kernel and run the kernel. And after that, we can bring the buffer back to the host. So zooming into the Mojo GPU compilation flow, so there are multiple stages, big stages for Mojo compilation. Mojo file source code goes through parser. We will first land into the parametric IR domain, where we will do semantics checks and some of preliminary optimization. And then we enter into the elaboration phase, which is similar to C++ template instantiation. So after that, all the parameters will be gone, all the IRs are concretized, and then we do more optimizations and then go to LLVM to generate binary code. So GPU compilation happens during elaboration phase because, as you can see in the previous slide, that a GPU kernel function is provided as a parameter to the enqueue function and compile that library interface. So before elaboration, we have everything in one MLIR module, both GPU code and the host code. So during elaboration, we know that we want to compile two kernels to NVIDIA backend. So we will slice these two kernels into a separate MLIR module, attach the target information, here is NVIDIA, to the module. And we will run through the whole compilation the same as the CPU side, just with a different target information. And then we will use our parallelizing LLVM backend to slice different kernels into separate LLVM module and then go to the kernel. So after this part, we will have here, we are trying to compile two kernels, and we will get two PTX for each of the kernel. And then we will plug in this compile the result as the return value of the kgen compile offload up so that we can consume it on the host side to either do print or go to launch the kernel to run it. So this is more or less what the compilation flow looks like. We can also control when we want to stop the compilation for the kernel to support debugging. We can say, oh, I want to see the LLVM IR, or do I want to see the assembly IR, or do I want to see the final object code? So this can all be controlled at the library level so that the library will tell the compiler when to stop. So as a conclusion, Mojo provides a unified way to write both CPU and GPU kernel in one language. So most of the features are driven by Mojo library as a Mojo code. That makes the compiler much simpler. We don't have to do a lot of heroic magic to accommodate the programming model. MLIR is very helpful here for us to have a seamless compiler integration that we can just add different ops to extend the capability of the compiler. We do not have to change the parser of the language. And we can also use upstream dialogues for like NVVM, RockDL, and LLVM directly plug it into the library because Mojo is also a syntax trigger for MLIR dialogues. So this approach is actually not just restricted to GPU. Generally, we believe that it's generally applicable to any other accelerators. As long as they have a LLVM backend, then it will be pretty much similar as this flow looks like. Or if it's based on MLIR, then we can plug in that as a Mojo DSL to support that. So all the Mojo GPU kernels today are open sourced, so you can see how we implement those performance kernels in the Mojo code. And we will be at the post session tomorrow, so come talk to us if you want to learn more about it. Thank you very much.